Next, we're going to look at the third type of probability, and that's called subjective. So a subjective probability results from intuition, an educated guess, or estimates. So it's basically sort of what do you know about the subject? What do you feel will happen? It's not as rigid as the other two. So for instance, given the patient's health and extent of injuries, a doctor may feel the patient has a 90% chance of full recovery, right? So that percent is based on the doctor's experience with the condition or with the surgery or injury, whatever they're dealing with, and also based on the patient's medical history, right? So they look at that and they give their best estimate for how well they think that patient is going to recover. Or a business analyst may predict that the chance of employees of a certain company going on strike is 0.25, right? So about 25%. So these are based on intuition, educated guesses, and estimates. It's still that idea of part to total, right? What's the likelihood of it happening? But it's a lot more, we'll say, fluid and not as rigid in the calculation. But like I mentioned, all three types, we still have this general idea of this part to total or finding the proportion when we're calculating probabilities. All right, so let's classify each statement as either classical, empirical, or subjective. So the first one is the probability that you will get an A on your next test. So that probability is a 0.9. So you have a 90%, you feel like you have a 90% chance of doing well on your next test. So this is a great example of a subjective probability, right? It's based on an educated guess. It's based on your own experience with the material. So maybe you feel pretty confident in the class, you've been doing your homework, you've been studying, so you feel pretty good that you have a good chance of getting an A on your next test. So it's subjective. For 2, the probability that a voter chosen at random will be younger than 35 years old is 0.3. So this is a great example of empirical data or empirical probability because it looks like it's based on some sort of survey that's been conducted or survey data from the real world, right? We kind of see this real world notion of voters being chosen at random based on, and choosing one that's younger than 35 years old, for instance. The last example is based on winning a 100-ticket raffle with one ticket is 1 out of 1,000. Now, this is your classical probability. So those probabilities are fixed. They're not based necessarily on like a survey or observations of real world data. If you think about it, if you have a 1,000-ticket raffle, meaning that you're selling 1,000 tickets, then every ticket has a 1 in 1,000 chance of selling. So that's just kind of an innate probability. So again, we see these a lot with things like raffles, lottery calculations, dice rolling, card games. So things that are just have an innate probability. So they have a very fixed total. It's easy to find the part there. And it's not necessarily based on real world data like empirical would be. Now, the probability of any event occurring is between 0 and 1 inclusive, meaning the endpoints are included here. If the probability of something is 1, the event is 100% certain to occur. If the probability is 0, the event is impossible. So we do use the values of 1 and 0 very carefully here. If you think it's very likely, but you're not 100% sure, then maybe we use 0.9 or 0.99, right? So 1 would be for certain and 0 is impossible. Sorry, this is a typo. This should be 0.5. A probability of 0.5 means there's an even chance the event, sorry about this, guys, has an even chance of occurring or not occurring, right? So it's a 50-50 split. That 0.5 probability represents 50%. If your probability is 0.75, so it's closer to that 1, then it's more likely to occur. If your probability is maybe 0.25, so closer to the 0, it's less likely to occur, right? So the higher your probability is, the more likely it's going to occur, and the less likely your probability is, or the smaller it is, the less likely it is to occur. Now, an event with a probability less than or 0.05 or less is typically considered unusual. So this is one of those big cutoffs that we're going to see a lot of times. There are different cutoffs we can use too, not just 0.05, but that tends to be a very common one. So if the probability is less than 0.05, it's typically considered unusual. And unusual events are unlikely to occur. And again, we're going to use this idea later when we talk more about inferential statistics. Now we also have complementary events. So when we have probabilities, the sum of all outcomes in a sample space is 1 or 100%. So when we take the probabilities all together of every single possible outcome occurring, you should get 100%. It's important. An important result of this fact is that when you know the probability of an event, you can find the probability of its complement. So that's its opposite, or the event not occurring, sort of. So the complement of event E is the set of all outcomes in a sample space that are not included in event E. So it's, again, the opposite idea. And the complement of an event is denoted by this. So it's like this little dash right there next to the E. And you can read it as E prime, or you can read it as the complement of E. And we can use Venn diagrams to show this if you find that picture helpful. So for instance, if this is our sample space, okay, so the whole thing here is our sample space, so all possible outcomes. If this is your event E, then this is your complement. So it's everything outside of E. Now what happens is when we add the probability of the event E and its complement, you should get 1 because it includes everything all together. So let's use the frequency distribution from example 7 and to find the probability of randomly selecting a social network user who is not 23 to 25 years old. So if I go back to that example, let me see if I can find it here for a second. So here was example 7. And we saw the probability of the user being 23 to 35 was 0.032. So the probability of this event occurring was, let's see, 0.32. And what we're looking for here is a probability that it does not occur. So we're looking for that A prime, so the complement, that it does not occur. Well, remember that the probability of the event plus the probability of its complement is going to always equal 1. So if I know one of these facts, 0.32, then I can use my solving techniques here, just like if I was solving an equation, to subtract and get that probability of the complement. So we get 0.68. So it's very easy for us to find a not idea if we already know the probability of the event occurring. We can just subtract it with 1 to find the other half. All right, so let's look at one last set of examples here. Okay, just doing some more applications here with probabilities. All right, so example 10. A probability experiment consists of tossing a coin and spinning a spinner that contains the numbers 1 through 8. So for instance, think about a game. If you've ever played a game before, a lot of times we have spinners, right? So you have this kind of, let's cut this into 8 pieces. Okay. So you have numbers 1 through 8 here. So maybe number 1, 8, 2, 7, 3, 6, 4, and 5. The order doesn't really matter at all. They could be in order. And so you have a spinner here. So if you've ever seen games like this, we often have spinners where you spin it around and see what number it lands on. So we have a spinner and we also have a coin that's being tossed. And of course, your coin is going to be either heads or tails, right? Okay. And so your spinner is either numbers 1, 2, 3, 4, 5, 6, 7, or 8. And everything is equally likely. So we're going to use a tree diagram to find the probability of each event. So let's do event A, tossing a tail and spinning an odd number. So the first thing we need to do is find the sample space. So before I can even answer these questions. So let's hold off for a second and let's look at the sample space. Okay. And again, we can use a tree diagram here. So you could get a head or you could get a tail, right? So that coin could either be heads or tails. And at the same time, for that spinner, you could get a 1, a 2, a 3, a 4, a 5, a 6, a 7, or a 8. And same thing for a tail. You could get a 1, a 2, a 3, a 4, a 5, 6, 7, or 8. So what our sample space looks like here is you could get a head in the number 1, heads in the number 2, heads in 3, heads in 4, heads in 5, heads in 6, heads in 7, heads in 8, tail 1, tail 2, tail 3, tail 4, tail 5, tail 6, tail 7, or tail 8. So there's our sample space. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 possible outcomes there. All right, so for event A, we're looking at the probability of tossing a tail and spinning an odd number. So I'm going to do this coloring blue. So tossing a tail, okay, so that's my tail, and spinning an odd number. So T1, T3, T5, or T7. So our probability there is it could occur 4 different ways, and there's 16 altogether. So we get 1/4 or 0.25. Now for event B, the probability of tossing a head or spinning a number greater than 3. So I'm going to use pink here. So here are our heads and a number greater than 3. So it could be the 4, the 5, the 6, the 7, or the 8. So I have 1, 2, 3, 4, 5 possibilities out of 16 altogether. Actually, sorry, let me pause for a second here. I read this too fast. So this word said and I was thinking the same thing. This said and, but this actually says or. So we have more possibilities here. And I apologize. So even I have to be careful when I read. So in the first case, it said and. So tossing a tail and spinning an odd number. So it was T1, 3, 5, and 7. And for me, I read this too fast and I was thinking and. But this actually says or. So other things can occur. Either tossing a head or spinning a number greater than 3. So we would just want at least one of these to occur. So tossing a head, there's actually 8 possibilities of getting a heads. Or spinning a number greater than 3. Well, we have these here, but we could also spin a tail 4, a tail 5, a tail 6, a tail 7, or a tail 8. So I apologize here. I have to be better about reading myself. That word or changes. Tossing a head, there are 8 chances. Or spinning a number greater than 3, there are an additional 1, 2, 3, 4, 5 chances. So altogether here, I actually have 13 chances for satisfying this event. And that gives me, let's see, about 0.813. All right. So just like with you guys, I have to slow down sometimes and reread things. So be careful of those words. That word and means I want both of these to occur at the same time. So a tail and an odd number gives me only 4 options. Here I use the word or, so I could get a head, which is 8 options, or I could spin a number greater than 3, which gives me another 5 options. So there are 13 ways to get that to be true. All right, last one. Your college identification number consists of 8 digits. Each digit can be 0 through 9, and each digit can be repeated. What is the probability of getting your college identification number when randomly generating 8 digits? Okay, so first of all, we need to figure out what the sample space here is. Now I have 8 digits, right? So it's 1, 2, 3, 4, 5, 6, 7, 8. Each of these can be the numbers 0 through 9, excuse me, and they can be repeated. So there's no restriction here on if I can repeat numbers or not. So for all of them. So for this first number, I have 10 choices here. And then I have 10 choices, 10 choices, 10 choices, all the way down the line. Now we can use our counting rule here. So I'm multiplying this 10 8 times. Or I can write this as 10 to the 8th. So our total here is actually 100 million different options. So what's the probability of getting your college identification number when randomly generating 8 digits? So getting it right, that one identification number right, well, the probability here, we'll call this event A, is a 1 out of 100 million chance. So point, let me count here, 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7, 1. Okay, so there's only one way to get the college identification number, and then there's 100 million chances. So you have a very small chance of it just randomly getting generated on its own the first time.